So in the previous video, we covered the macroscopic galvanic cells, right? So we looked into the concept, and just to remind you what exactly to comprise a macroscopic galvanic cell, you need two electrodes, right? Anode and cathode. You need them to be connected by an electrical wire, or they just have to be in the direct contact, right? Because that would eliminate the need for the electric wire. And then the final component that you need is the electrolyte, right? Up to this point, we looked at the problems where electrolyte was always 1 mole, okay? And if you go back to all of the previous problems, you will notice that every single time we looked at the electrolyte that was 1 mole. What happens that when the concentration, the molar concentration of electrolyte is not one, right? Let's say below one. So let's consider that. We're looking now at the galvanic cell, which is no different from the one that we saw before. Okay. So we're looking at the galvanic cell, but this time we're looking at the electrolytes with molar concentration, which is not 1 mole, right? And then I will give you the answer right away. So, and then I'll explain you why. Um, well, whenever you have an electrolyte whose molar concentration is less than one, the driving force for corrosion is actually greater. Okay. Why? Because there will be a more negative EMF, right? The more negative potential. So I'm looking at this reaction here. M stands for any metal, right? It could be zinc, aluminum, it doesn't matter. But what happens is that if the concentration is actually less than one, you will end up with the potential that is more negative than the standard potential that we saw in the table. And is it possible to measure something like that? Yes, by using the Nernst equation. And I want you to look at this equation, and right away, let's go first step by step what is included in there. First, you have this E naught, right? That is the standard EMF of half cell. Well, what does it mean? These are these numbers from this table, right? That's what you were used to, because everything here was estimated for 1 molar solution, okay? Now, if your electrolyte is not 1 mole, you need to add whatever comes after the plus sign. And there are just few things. This N is the number of electrons transferred. Examples for zinc, it's going to be 2. For silver, it's going to be 1. How can you find it? If you do not recall the valences, which is pretty tolerable, right? But in here, you can easily find it. Let's say if I'm looking at the copper and I do not remember the valence, it gives me a guess in this table, right? And you can find it for lead, nickel, and cadmium, iron. Keep in mind that there are two separate irons, right? We usually assume that it's iron 2 plus unless I specify it in the question that it is something different. And then the C is going to be the molar concentration of ions. Now, I want you to first, let's look at this component here, this log, right? What does our log typically look like? Well, if this is my concentration, this is going to be my log C, then this looks like that, right? And I know that the logarithm is equal to 0 when your concentration is equal to 1, right? So if my concentration is equal to 1, then my log is equal to 0, right? So once again, if this concentration is 1 mole, then my entire log goes to 0, and that means this entire thing goes to 0, and I end up with just this equation, meaning that I don't have to calculate. There's no need for me to use the Nernst equation. I just go into the table and I pull up the number from there. So hopefully that makes sense, okay? But if the concentration is not 1, that means I have to adjust my the potential of the half cell, right? So let me go back. So hopefully you guys understand where it comes from. Oops. So if this is my 1. Now, going back to where it says that the driving force of corrosion is greater, and specifically the potential is going to be more negative. This happens when your concentration is actually less than one, right? Because I want you to think about it. I'm going to use a different color so it makes sense. If my concentration is going to be less than one, so if I am to take numbers in this range that I'm now highlighting with purple marker, okay, well, if I am to take any of those numbers, right, my corresponding numbers is going to be here, right? So my logarithm of this function, of this concentration, is actually always below zero. It's going to be somewhere from here, right? And it means I have my E naught, okay, minus something negative, right? And this is why you have a more negative EMF, okay? So this is just something to keep in mind. I actually will have a really good example to show you later. And whenever I refer to the concentration here, I'm referring to the molar concentrations of iron in the electrolyte, okay? Now, what happens if I have no ions, okay? Uh, So far, we looked at all of the examples and we had ions present, right? The majority of the examples we looked at. What happens if there are no ions? And then I would also like to break it down into two possible solutions. I would like to look into the scenario where my electrolyte is acidic, and I want to look into the scenario when my electrolyte is actually basic or neutral, right? So what happens to my cathode and what happens to my anode, okay? So let's look at the example here. Let's first set it up so we understand what we're looking at. I'm connecting an iron anode, right? Well, it already says it's iron, and I'm connecting it to copper, okay? And the electron is going to flow this way. Before we assume it as is, right? Maybe I have some perfectionists listening to this video, and you probably have the desire to go back and actually make sure that if you connect iron and copper, iron is actually anodic, right? So let's find the iron. We assume that this is the iron right here, and the potential is negative 0.45. Now I'm linking it to copper, which is positive, and it's going to be 0.34. So indeed, the electrons will flow toward copper, and then the anode here is my iron. Again, by definition, we always assume that we're working with iron 2 plus, unless we have knowledge to understand that it's different, something like iron 3 plus. Okay, so this is the scenario I have. Now, in my electrolyte, I want you to keep in mind is that there are no ions, right? So there's no copper to electroplate on my copper, okay? I have three scenarios. I can either have acid or I can have basic neutral environment, okay? Well, to begin with, we just identified that my iron is going to be the anode, so this is what's happening on the iron. And regardless what the electrolyte is, whether it's acid or basic or neutral, my iron is going to corrode just like this equation, right? I'm going to have a typical iron oxidation, okay? But what's going to happen with my at the cathode? Well, the reaction at the cathode will depend on your electrolyte. Okay, so if acid, right, you're gonna end up with the reaction that we've already seen before, where you have basically the generation of hydrogen gas, right? Because I'm looking at the acid, right? That means I have a bunch of my hydrogen ions in there that are ready to consume the electrons and produce the hydrogen. Now, what if I have acid, right? If I have, oops, I thought I had a pencil. Now I have acid with an oxidizing agent, and that means that it has an oxygen in there, then your reaction is going to be like this. And I want you to see that now you're looking at the exact same reaction, right? And of course you will notice that the coefficients did change, but you still have your hydrogen ions, right? And then you have your electrons, and now you need to add the oxygen because you have an oxidizing agent. And what's going to happen is that here you will be producing water. Okay, now what happens if I have a basic or neutral, right? Basic or neutral. Okay, this is where I'm looking at the scenario with like water. So in here, you will have oxygen you will have oxygen, water, your electrons, and you will be producing hydroxyl groups. Okay, I could just say, all right, moving on, but it is paramount because in quite a few questions within this course, I may ask you to write down the reaction. And it's not even about this course, right? As we already know that oxidation and reduction reactions, they happen at the same rate, okay? And that is really important. And the reason it is important is that means that I can you don't have to target the oxidation, right? The corrosion of iron or zinc. Sometimes it is very, very smart to actually control the reduction reaction, right? Because if you know that that reaction needs oxygen, but then you're going to deplete the reaction of oxygen, you're going to quench reduction. So if I quench reduction, that means my oxidation doesn't happen either, right? And so this is why I am not trying to drill you into something that you won't need. I'm actually trying you to memorize these reactions because if you know what the reaction is, as an engineer, you can start thinking, okay, then how do I control it, right? Because it's a reaction, meaning it's just the temperature and it's just the products and reactants, right? And if I can start twisting one of those, I can control the corrosion process in general. Okay, so I would like to draw something. Hopefully, I chose the best format to represent it because the idea is I would like you to have it on your equation sheet and maybe you can figure out a better way to display it, but for now, I will do it the following way. So we already know that for the oxidation reaction, it's always the same, right? For the oxidation reaction, it's your metal that goes to metal and plus n electrons, right? This is what actually happens to like any metal, and it doesn't matter. But for the cathode, right, things do get complicated because it depends on the electrolyte. So let's say if I have acid, right, the next question that I should ask is that I'm gonna ask first is oxygen. Is oxygen present? Because if I have acid with an oxidizer in there, the reaction is different when I have an acid without an oxidizing agent, right? So from here, if it's yes, or perhaps, well, naturally you shall, nope, I'll say no. I'll start with an easy one because I want to kind of like build on top of each other, right? So if there is no oxidizer, I just have my hydrogens floating around there, ready to accept my electrons that I delivered from my metal. And then what happens is that I have a generation of gas. Now let's balance it out. I don't like how I did not leave space for balancing things out. So it's going to be like this, right? Okay, so we've seen that before. This is something we're familiar with. Now, what if the answer is no? What if the answer now is yes, there is oxygen? That means I have to start with oxygen, and then I still have my these hydrogens and I still have my electrons because it is still acid, right? And the acid, it's an abundance of hydrogen ions, right? So what do I get from here? Well, the only thing I can get from here is H2O, right? Um, H2O. Okay, now let's balance it out. It looks like I have to have 2 in here. That means I have to have 4 in here and 4 in here. I do not like how I am not leaving a space for balancing it out. So once again, you will notice that this portion, right, is identical to here, but now you have to add the oxygen. Yes, the final product changes. You go from hydrogen to water, but the rest is just balancing out the equation. You don't have to memorize it. Hopefully, you can actually, once you understand it, you should be able to derive it. And the final step is going to be just balancing it out. Now, what happens if I'm working with basic or neutral? Okay. So what is going to be the equation here? Well, I'm going to have oxygen, I'm going to have water, and of course I got to have my electrons, right? And then in the end, what I'm producing here is the hydroxyl groups, OH, okay? And so let me balance it out. It looks like if I have to put 4 in here, I have to put 2 in here, and then I'll have 4 electrons in here, right? And this is how we come up with this reaction, okay? So again, practice on your own, get very comfortable with it because it is important, right? And as I said, guys, just think about it, right? If I'm looking at this basic and neutral reaction, right? And as I said, this is your cathode, right? But let's say you have a metal, right, that is standing in a basic neutral environment and you're trying to prevent its corrosion, right? We will look into other things, but just within this specific example, just purging oxygen out of the solution, right? Just or putting some scavenger that can hunt and eat your oxygen, right? Just that alone is gonna slow down your cathodic reaction. And if it slows down your cathodic reaction, automatically you slow down the oxidation reaction, and your whatever iron pipe or whatever has to stand in the water is going to be fine, right? So it's not always that simple. You usually have to always be on the lookout at like so many factors. But this is just as an example why, as an engineer, you should be familiar with the reaction, regardless how painful it is. And again, things are painful only when you attempt learning and trying these things on the first time, right? The more we do that, the more we solve problems, the more comfortable we get with the corrosion problems and things like that, right? And any engineering problem. Now, I know that so far I was constantly drawing your attention to a galvanic cell where you have two metals together. But now, if you think about it, and now you will be actually paying attention to things you see outside of your house. A lot of you will actually go down in the basement. I know a lot of students who started looking into their dorms and their grandparents' houses. You'll see a lot of pieces pieced together that should not be pieced together because you'll see one is corroding aggressively. We'll get there. But what you're thinking probably now that not necessarily I sometimes piece things together. Sometimes I'm just looking at the pipe, right? I'm just looking at this iron pipe outside of my house and I see that it's corroding. Or you have a tank in your garden, in your backyard, you have a tank filled with water and you see that your tank is corroding. It's not attached to anything, right? It's just a single electrode. So what happens there? Guys, the process is very simple. And I already mentioned to you, and I'll scroll back and I'll show you where exactly I mentioned it. You don't need to connect something to another metal for the metal to corrode. Unfortunately, for all of us, right? You can have a microscopic galvanic cell, and that means you have a local anode and a local cathode, right? And we call it those microscopic cathodes and anodes. And I'll go back to where I draw originally, early on, when I was dissolving zinc, right? Right in here. This is your microscopic cell, right? Galvanic cell. Let's think about it. Where I have it highlighted in green, that is my anode because I have a dissolution of zinc, right? Now, the purple space in there where you have the reduction of hydrogen, that is going to be your local cathode. Are these two inside the electrolyte? Yes. Are these two connected? Yes, they are connected by the metal piece. So there's your galvanic cell. So that means that things are actually a lot more dangerous than we think about it, right? It's not about just avoiding dissimilar metals, right? That's not enough. Apparently, I can have a galvanic cell on any metal, right? And often these things are, and later on I'll give you a bunch of beautiful examples. Um, you can set up a galvanic cell just due to structural irregularity, just that alone. If you have a certain imperfection in your material, that alone will set up a galvanic cell. The structural irregularity could be also on a microscopic level. I'm about to show you plenty of examples. In here, I'm showing you the example of actually iron corroding. It's a bit more complex process. It's not as simple as I described you before, right? Well, it starts very simple, but then you can see that there are additional reactions. At no point I will ask you to memorize it or show it to me. I do not see the necessity of it, but I do want you to understand the beginning of the corrosion, right? When it kicks in. But in example here, I will still show you, since we did discuss it before. Here's your local anode, right? and then I'll switch the color. This is going to be your local cathode, right? This is zinc in hydrochloric solution. It's a single electrode, right? But it's going to be corroding, and it's going to be corroding very fast because you have everything that takes you created an environment, right? You dropped it in the hydrochloric solution. If you remove the hydrochloric solution, right? If you remove electrolyte, things will slow down drastically, right? Because you don't have these available hydrogen ions for the cathodic reaction to run. Right? Now, if I am to look at iron, here's my iron, right? This is going to be where I should keep the same colors, right? This is going to be where my anodic reaction is. This is where you have a dissolution. And right in here, it's just it's not necessarily larger in space. It's just took authors to draw it larger. But that's how you will have your cathodic reaction happening, right? So once again, I want you to understand what a galvanic cell is, macroscopic galvanic cell, because you need to understand, it would make sense for me to go back to the galvanic cell that I drew. I used zinc copper, right? Just as your authors. It makes sense to understand this because if you understand this, you understand the macroscopic galvanic cell, right? When you have two electrodes directly connected through electric wire. I keep repeating it because at some point you guys have to assemble. At some point you will be corroding elements within this course. And whenever I see students trying to connect galvanic cell, they do a lot of weird stuff. The concept is very simple. Even though they understand the concept, you have to have two electrodes. You have to connect them, and then you have to put them in the electrolyte, right? That's the macroscopic galvanic cell. But we don't, for the corrosion to occur, you don't need to have actually two separate electrodes. Once again, the corrosion can happen on a single electrode, and the only difference here is that your anode and cathode are now microscopic, right? And that's why we call them local, okay? All right, so hopefully I kind of like hammered the point. Let's solve a few cool problems that allow you to start practicing your knowledge in terms of, okay, where's the cathode, where's the anode, and what kind of reaction happens. And again, I will emphasize it why you want to know what kind of reaction is happening. Because if you know the reaction, you can take advantage of controlling it, right? We can't control unknown, right? But we can control the known. All right, so, and this question actually asks you to write the anodic reaction and cathodic half-cell reactions for the following electrode-electrolyte conditions. Okay, well, let's start from number one, okay? And I want you to assume here, if occasionally I forget to say connected by an external wire, you just have to assume that they are connected, right? Because it's just me omitting it, right? Okay, so I have copper and zinc in a dilute copperic sulfate solution. Okay, so what is it? Copper SO4, right? Copperic sulfate, yes. All right, and I have a copper and I have a zinc. All right, guys. Well, first, let's connect those two, copper and zinc. I'm not going to assume that you remember by heart. I'm just going to guide you how you would be able to answer the questions. And then I'm going into copper and zinc, right? And you will notice that zinc is right here at the bottom, and it's going to be, well, a lot lower at negative 0.76. You will probably know it by heart at some point. And then copper is 0.34. So if I am to link zinc and copper, zinc is my anode. Okay, so that means that I can begin with writing the anodic reaction. So my anode, right? Anode is going to be, oops, zinc dissolving, zinc 2 plus 2 electrons, right? Okay, so what's going to happen with my cathode, right? I know that my copper is a cathode. Will I have copper electroplating back? Well, technically, yes, because I will have my copper 2 plus and I will have my copper 2 sulfate ion 2 minus, right? SO4 2 minus. Because I have available copper floating everywhere in the solution, that copper is ready to accept the electrons and electroplate back on my copper electrode, right? So that means that That means that my reaction on the cathode is copper 2 plus 2 electrons, and this will produce copper. Okay? So next, question number 2. I have a copper electrode immersed in an oxygenated water solution. All right, well, copper will be dissolving, right? So it's going to be copper going to 2 plus 2 electrons. Now, again, if you don't remember, well, is it copper plus or 2 plus, it's not good. However, at this point, whenever you have a question, you just go back to the table. And during any graded assignment, and that includes let's say exam or something like that, right? I will always ensure that the table is going to be always next to you, so you'll be able to look at the table in case if you forget what the number is, what the valence is, what the reaction is, and things like that, right? And now I have oxygenated water solution, right? So that means, well, I just realized that I forgot to write down that this is, I'm going to be specifying it every single time, because if you ever, when time goes by, I want you to be able to look at the notes and still remember where the anode, where the cathode is, right? Now, the cathode is going to be, okay, so I'm looking at the um, water solution, right? Basic water solution. So it's going to be O2 plus H2O plus electrons, and I will be producing hydroxyl groups and 4, 2, 4, right? Let's say if this is something that you don't remember, how would I solve this problem? Well, I'm going to go back to this. And this is exactly where it says, because I don't have any ions present, right? So perhaps I should have said no ions present, right? And that's exactly this scenario, right? You don't have any ions present, and that's where you go either with acid or the basic, okay? So hopefully that makes sense. And I'm taking this equation from here. Now, going back, moving on to the third question. We have an iron electrode immersed in an oxygenated water solution. Easy, right? Well, first, I'm going to assume that my iron is 2 plus because that's what I assume, unless I'm given either information. And then in here, I will actually have, I forgot to write down anode again. I should stay diligent, it's really important because I know that if I don't write it, you won't be writing it either. And cathode, the beauty of it, copy, the beauty of its technology, paste, right? Same. And then number 4, give me something challenging, right? Things seem to be a bit more straightforward. Okay, number 4, magnesium and iron. Ooh, love it, right? So I'm looking at new metal here, magnesium and iron. We're going to assume that this is iron 2 plus. Connected by an external wire, and they are immersed in an oxygenated 1% sodium chloride solution. That's a salt, right? So it's in a 1% salty water. Love it, right? That's a good question. Okay, so well, first we need to find the anode, right? And this time we have iron and magnesium. Let's go back to our standard electrode half cell potential. Which color shall I use, guys? I'm gonna use orange, okay? Let's find magnesium. Magnesium is right here, and I will highlight it twice. And you guys will see that magnesium corrodes fast, and magnesium corrodes well. And trust me, at some point in this course, I will actually give you beautiful examples of why you can use that to your benefit, knowing that magnesium corrodes really fast, okay? So magnesium is negative 0.237, and then I know that below this is just potassium and lithium, so clearly iron is above. Iron 2 plus is here, right, which is negative 0.45. So if I am to link those two, I have no doubt that my magnesium is going to be anodic, right? And the reaction is going to be magnesium goes to magnesium 2 plus 2 electrons, okay? So going in here, and anode is going to be magnesium, goes to magnesium 2 plus plus 2 electrons. So hopefully you are all on the same page with me with this conclusion. And then cathode. Okay, so well, iron is a cathode, right? But will iron electroplate? Well, not really, right? Because I don't have it. If you are to look at what I have oxygen and I have 1% of salt, and then the rest is obviously water, right? I have a salty water. So in a sense, it's the same as oxygenated water solution. And the thing is, I will of course cheat my way by using the advantage of technologies that I have in my hand. Okay, this is going to be my cathodic reaction. Um, I was about to say something. I forgot. My thought evaded me. Magnesium, iron. I looked in this. Oh, the salt, the salt, right? The presence of salt will change the outcome. And specifically, so hopefully people remember, is that salt, we add additional ions, right, such as sodium and chlorine. And those two, they're going to accelerate the transfer of electrons. And this is why whenever the city workers are trying to dissolve ice because ice is extremely dangerous, right? It leads to a lot of collisions, and we have to get rid of the ice because, trust me, regardless of how many warnings are sent to people, people will still take their vehicle and they will go on the highway. And this is why we need to spread the salt and create a eutectic alloy, right? So hopefully you remember that to allow the mixture to start melting below 0 degrees temperatures. I always operate in degrees C, so keep that in mind whenever I use temperatures. Um, but a lot of people that own a car, they know that that's danger, right? Because if you deposit any salt on your metal, right, what happens is that you basically, the electron transfer is now a lot more efficient, right? And that's why the material that is constantly subjected to salt water actually corrodes faster than the material that is subjected to the water without the salt, due to the fact that this conductivity, the electrons are transferred a lot faster, right? And in a sense, you are accelerating oxidation. You are accelerating oxidation. Well, it doesn't matter. Or cathodic reaction, you see it right there. Like I'm referring to either this or this. These two are transferred a lot faster because the addition of salt ions improves the conductivity of the solution in general. All right, I have a few more things for you, and I also would like to point out what happens to the ion concentration galvanic cells, okay? And at some point, I did say that galvanic cell, it's two different dissimilar electrodes, right? This is what I kept saying, is that you can have something that operates as a cathode and you can have something that operates as the anode, right? But now, and a lot of you may be thinking that, well, just take two the same, right? If pairing aluminum and iron is a problem, right? Because that will corrode iron, right? Then pair iron and iron. And I want to give you an example where you do pair iron and iron, but somehow you still will have one as an anode and another one as a cathode. And I will give you an example of how this may occur. There are multiple examples like that, but we will start with the first example. It comes down to ion concentration. Okay, and by ion concentration, I mean this concentration of your iron 2 plus, right? Envision that on one side you have a low, on the left hand side, I have a low concentration of iron 2 plus, and then on the right hand side, I actually added more. Now, because we've seen before this Nernst equation, and I will just give you an example. What's going to happen to the potential? I know that the lower the concentration, right, the more negative the potential is. And I'm going to take into consideration the concentration of like 1 millimole versus 0.01 mole, right? And if you ought to plug in the math, I'm not going to be doing it, but you guys also, this would be the constant, the potential if the concentration was 1 mole, right? But if the concentration is dropping and we're plugging it in into the log, right? You will see that for the right hand side where you have a higher concentration of iron oxide, you have a negative zero point 0.5, and on the left hand side you have a negative zero point 0.5. So all of a sudden there is a gradient, right? So even though both electrodes are made out of exact same iron, they are now dissimilar. They act as dissimilar because they have a different potential. And the way the potential difference is established is by the iron concentration, iron, iron concentration. That was a bit hard to pronounce. But so hopefully that makes sense, right? So and that's one thing to keep in mind, right? So using same material is always beneficial whenever we link metals together, right? Because you are avoiding the macroscopic galvanic potential, but you still, whenever you are dealing with electrolytes, you still have to be aware of the fact that you can have same material or electrodes made out of same material behave as anode and cathode just because of a difference in the ion concentration in the electrolyte, right? And obviously the one that is more negative is going to be your anode, and the one that is more positive is going to be your cathode, right? And there's a bit more than that, and perhaps something that we encounter very often. And at some point in one of your projects, you will have to walk out in the world and you will have to spot the corrosion and identify the mechanism and identify the type of corrosion. This is the type of corrosion you'll be looking for quite a bit. And it's called the oxygen concentration cell, okay? And I want you to think of the following. I have two electrodes, right? And again, we're going to keep the same, okay? We're going to keep iron. But I want you to think of the following, is that now the difference in the electrolytes is that one electrolyte has low oxygen and another one has high oxygen. Okay, so if I'm going back in here, it's going to be almost the same, but forget about the iron concentration. Think of oxygen. One has abundance and another one is depleted, right? And the question is, what's going to happen? I will tell you right away. It's going to be a galvanic cell, right? Because it says right here, it's a cell and it's called an oxygen concentration cell. And one electrode it will corrode, and another one will act as an anode, and another one will act as a cathode. This would be a good time for you to just use your knowledge about the chemical reactions, right? The half cell reactions, to think, well, which one will be cathodic and which one will be anodic, right? Now, I'm going to assume that you're pausing the video and trying to brainstorm. This is a beautiful question. And now I will give you the answer. The area where you have the abundance of oxygen will be your cathode. The area where you have less oxygen is going to corrode. And now you would probably think, why, right? Especially if your answer was different from mine. Because I want you to look at this specific example, right? Oxygen is needed, right? Because on my anode, my reaction is this. It's just dissolution of metal, right? Metal is there. Metal is on either side. Metal is dissolving. But the cathode reaction runs where you have the oxygen, right? And that means the abundance, where you have the abundance of oxygen is going to be actually where you have your cathode. And before I go on to my whatever the slide that has the answer, I want you to envision the following example. I'm going to give you an example, and it's called a water line corrosion. At some point, I will show you examples. I want you to think of the boat. Okay, this is going to be my boat, and you have this water. You have this water. Okay. And I'm sure that, how do I choose a yellow color? I don't have a yellow color. I have to use a red color. I'm trying to show you the rust. If you think about the boat, you will notice, yeah, that's true. I always see it. There's like a specific line of corrosion. And guys, where it happens? It's going to happen right here, right underneath. And I'll explain you why. Because what happens is that the concentration of oxygen is always higher above the water, okay? But right below, just like tiny below, you actually has a depletion. And because these are two are in contact, right? You have an iron. So this would be your galvanic cell. This is my galvanic cell, okay? And then in here, I have my, right above the water, I have my cathode. And in here, I have my anode because there's only a certain amount of oxygen that is dissolved in water. And this is how we have like this perfect scenario. And it's just this water line, right? This is where you see the gradient. I'm not talking about anywhere below because it's going to be a bit different. I'm talking about the water line. And that's why you see like a line. A line of very explicit aggressive corrosion. It happens due to the fact that you have a galvanic cell, right? And the galvanic cell is created by the oxygen concentration. If you ever go next to the bridge where you have towers standing in the water, you'll see the same thing. You'll see a ring. It's like right under the water, and it's a very, very aggressive corrosion. Okay, so um, there's this is just an example. Now I will show you another example. We often, whenever you guys have this oxygen concentration cell, we talk about crevice corrosion, right? And whenever you guys have any crevice, and that means that you have like this stagnant pool of water and it's standing, and that's how you create basically inside the water you have less oxygen, outside you have more. So right in that crevice you will always, where you have the depleted zone, you will see a bunch of corrosion. That's why you see a bunch of corrosion. Corrosion peaks out, but underneath we don't see it yet, but I'm sure that if we ought to remove that bolt and the nut, you'll be surprised. There's going to be a huge ring of the material that is entirely disintegrated. You can scrape it with your nail. That's how weak it is, right? And once again, the reason this happens, right, this specific type of corrosion, crevice, later on I'll show you a bunch of examples and you will be able to identify the crevice corrosion. This is same material. If you are to look at this material, you see that the plate, the nut, the bolt are all made of the same material. I know for a fact that this is made out of same material. And so the engineer that probably did it, they probably thought, beautiful, there's going to be no galvanic cell. But in reality, they created an oxygen galvanic cell, right? Because the water is very, very small. The molecule, it's very, very tiny. And and I'm talking not about the rain, I'm not talking about the water droplets, right? I'm talking about the water, the moisture that is just in the air. That water is going to sip in there, right? And all of a sudden you have electrolyte, and now you have two electrodes in a perfect direct contact, right? There's a tiny bit of an electrolyte, and this is going to be, even though it's the same material, the gradient in potential is going to exist due to the oxygen concentration difference, right? Because underneath the plate, I have none, right? And outside, I have an abundance. And so that means that outside is my cathode, inside is my anode, inside is going to be corroding, right? So to summarize, since cathode reaction requires oxygen, right, and electrons, high concentration oxygen is cathode, right? Please keep that in mind. Every single time I explain it to my students and every single time I give them an example, everybody else flips it. Everybody else, for some reason, assumes that oxygen is the problem, and that means corrosion. Oxygen is the problem. But corrosion happens where you have areas depleted of oxygen. So please remember that. Now, a little bit more on the galvanic cell. At some point, I did say that galvanic cell, the microscopic galvanic cell within the same material, can exist due to imperfections, inhomogeneity. And guess what? We're back to grain boundaries, right? Well, first, let's start with good stuff that we know about the grain boundaries. We found out that grain boundaries are extremely powerful and are extremely useful because they have the ability to increase the tensile strength of the material, right? We know that. Why? Because they prevent the dislocation movement, right? They stop the dislocation movement. And that means that they make material very stiff, very strong. That's the great news. But however, and we know that the higher the density of grain boundaries, the stronger the material is, but there is an issue with it. Grain boundaries, believe it or not, but they are typically, in most materials, are more anodic. And that is the problem. So guys, what happens is that right now I have this grain A, right? This is my grain A, and this is my grain B. And they do have this grain area. And this area in here is more anodic with respect to either of the grain itself. So the grain boundary is more anodic with respect to the either of the grains. And what's going to happen is that there's going to be a corrosion happening at the grain boundary. And that means that the material will be, so if you were to set up an experiment where you can visualize it under the microscope, the distance in the grain boundaries, right? This distance is going to get bigger and bigger because it's going to be like, it will look like a empty space because the material disintegrates. And you guys can imagine that this type of corrosion is going to be extremely dangerous, right? Because while it happens at the boundaries, right? I'm looking at these boundaries, right, that are shown in the image. That's because this image has been, this is probably atomic force microscope, right? That allows me to use a very powerful microscope. To a naked eye, my material looks the same. So if I am not aware that the corrosion is happening, then when the danger happens, it's going to be too late. When the material will yield, it's going to be too late. This is why you just need to be in general aware that whenever there's a compromise, right? If you increase the density of grain boundaries, you make the material stronger. But if you know that the material has to serve in the environment where it needs a high corrosion resistance, you need to be very smart when you choose the material, right? Because right away you know that the polycrystalline material is more susceptible to corrosion because the grain boundaries are more anodic with respect to the grains. Now, perhaps I shall say something that occasionally you can have it flipped, meaning that your grain boundary is cathode, right? An example right here. So the grain boundary is cathode, and actually the regions adjacent to the grain boundaries are anodes. And why that happens, and I'll give you an example. Um, Sometimes you can have an alloy, right? And you guys remember that's when, again, we use an alloy to increase the strength. And usually we always use an alloy because alloy allows us to significantly increase the strength of pure metals. But what happens is that the solute, okay, the solute is what I'm doping it with. Solvent is the host. Solute is what I'm putting in. It can segregate. So that means and it usually happens that it segregates toward the like the grain boundary. It's kind of like one of the ways to think about it. It falls out of metal and it goes into the boundary. And that solute can be more cathodic with respect to the grain boundary. So, and that's going to be the scenario like this. Because the solute that comes out, let's say carbon. Carbon is more cathodic than iron, okay? And you have to be aware of this too. So that means whenever we do the doping, we really need to make sure that we disperse the solute equally, right? It has to be homogeneous. You don't want to end up with these areas where you have more carbon here and less carbon there. The moment you have it, you have a beautiful anode and you have a beautiful cathode, and there's going to be a galvanic cell going on full force, degrading your material, right? Now, multi-phase electrochemical cells. We already know what the phase is, right? And we know that sometimes you can actually develop an alloy that has multiple phases. And I will show you guys the example right away. In the image to the right, you see it's a pearlite gray cast iron, okay? Well, what it means is that it has like these graphite flakes. These are the darker regions, those darker channels. This is your graphite. Graphite, you guys remember that's made out of carbon, right? Pure carbon. That's the pencil. That's what it is, right? And then outside, it has the pearlite matrix, right? And whenever you have something like that, that is another concern for corrosion because you have electrochemical cell, galvanic cell, and the reason it is created is because you have certain phase that is more cathodic, such as graphite flake, adjacent directly to your pearlite matrix, which is anodic. And that pearlite anodic, right? This perlite will corrode. And again, that happens, guys, at the microscopic level. That means that the material will be, as the corrosion persists, you won't be able to spot it with the naked eye till the structure collapses, right? Till the integrity is lost. So this is why steel, and specifically in martensitic condition, which is basically, think of it as a single phase, has better corrosion resistance. And so usually as an engineer, you just have to be aware of all of these things that, okay, yes, I can increase the strength by introducing dopants, right? But I have to be aware that if I end up with a multi-phase alloy, doesn't matter how strong it is, if it has to serve in the environment where it requires corrosion resistance, do not put that material in there because you are setting up the material for a failure, right? And whenever you have, let's say, certain impurities in metal that can also precipitate out of the metallic phases, right? Whenever you have like this segregation, you have certain impurity that traveled and made an island next to a metal. Right away, you will end up with cathodic attached to anodic, and you're going to have an electrochemical cell. Now, well, at this point, I think we've covered enough, and the whole purpose of these two videos was to introduce you to electrochemical cells. And you need to be mindful of the most important fact is that, yes, there's a microscopic galvanic cell that requires two electrodes, two dissimilar metals, right, connected by the wire and standing in the electrolyte. That is a macroscopic version, but the electrochemical cell can exist at the microscopic level within the same metal, right? Then it can exist due to the impurity, due to the segregation of certain material falling out of the another material, due to the grain boundaries, right? Grain boundaries are typically more anodic than cathodic. Sometimes vice versa. If you have something leaking into the grain boundary can actually become more cathodic with respect to anodic. So just something to be aware of. But again, these two videos, they all come down to understanding the concept of the galvanic cell, whether microscopic or macroscopic.